This presentation will deal with half-life calculations and also tests that we use half-life to solve. We will calculate kinetic parameters for decay processes, including half-life, and we will describe common radiometric dating techniques. Okay, so we're going to get into the topic of half-lives. You recall way back in the chapter on kinetics, we had zero order, first order, and second order reactions. All radioactive decays are first order kinetics, every single one, and they all happen spontaneously. So our delta G is negative. Half-life, if you recall, was the amount of time to lose 1/2 of the mass of the thing, or number of moles, because quantity is proportional. Anyway, so for a first order reaction, T1F is equal to natural log of 2, or 0.693, over lambda. Okay, so lambda is the radioactive decay constant. It's also related via n of t, which is the number of things is equal to, the number of things at any given time is equal to n naught, n at 0, so how much you started with, times e to the negative decay constant times time. Okay, so we have a relationship between both the number of particles and the time it takes to decay, and also our rate of decay and how long it takes to go down by half. So we're going to use those in calculations. All right, so let's try a half-life calculation. The half-life of bismuth-210 is 5.012 days. What is the decay constant for the radioactive disintegration of bismuth-210? So that decay constant is our lambda, lowercase lambda. So we pull back up that equation, we solve it for the lambda. Lambda equals natural log of 2 over T1/2. Okay, our T1/2 is 5.012 days. So we go ahead and plug that in, and we get a radioactive decay constant of 0.1383 per day. If we want to calculate the fraction of bismuth, 210 remaining after 22 days, we take our n of t equation from the previous slide, we rearrange it so that we solve for the fraction, n of t over n naught. And you go ahead and you plug in the numbers. So we have t is 22 days and our lambda is 0.1383, and we get 0.04771. So that's the fraction that's remaining after 22 days. Okay, if you wanted to know percentage, you would multiply that fraction by 100. So about 4.771% is left after 22 days. How long does it take for a sample to disintegrate to 3.5%? Aha, okay, so if we have a percentage, again, we can go from percentage to fraction pretty easily. We just divide by 100. So we're going to go ahead and do that. Our n of t over n naught is going to be 0.035. And then we have that same e to the negative lambda t. And we're solving for t. So we put in our e, we put in our lambda, and we're going to do a little bit of algebra here. So at this point, we know that we have to take the natural log of both sides, and then we have to solve for t. And I get 24.24 days. Takes 24.24 days to get down to 3.5%. So it should be more time than it takes to get to the 4.7% we calculated earlier, and it is, so that made sense. Hooray, it works. All right, so this brings us to a practical application of radioactive material, and that is radiocarbon dating. So cosmic rays produce carbon-14 from the stable nuclide nitrogen-14. So nitrogen-14 is stable, but when it gets hit by cosmic rays, it can pop out a proton and produce carbon-14. Well, most of the carbon that is in the atmosphere, which is where these cosmic rays are hitting, is actually carbon dioxide. So the carbon dioxide gets pulled in by trees in order to go through photosynthesis. The photosynthesis makes nice cellulose and starches, which animals eat. And as a result, living things have a fairly constant rate of carbon-14 in their bodies, to carbon-14 to carbon-12, the ratio. And we can measure that, and we can figure out how old something is. Now, the complicating factor here is that because of the massive amount of emissions that we have put out of carbon-12, because when you burn stuff, it's been dead for a long time, and it has less carbon-14 than we started with, we are changing the ratio, physically changing the ratio right now of carbon-12 to carbon-14 in people's bodies. So our accuracy, sans carefully measuring this effect, for things that are recent for radiocarbon dating, is going down. Cool beans. Anyway, so carbon-14 emits beta decay, and it has a half-life of 5,730 years. So about 3 half-lives in, we stop being able to do anything with radiocarbon dating because it's just, we wouldn't be sensitive enough to tell the difference. So the outer limits sort of how accurate we can be is somewhere around 50,000 years. Really good accuracy, closer to 30,000. Okay, we can actually do more types of radioactive dating than radiocarbon dating. You can use other elements as well. So geologists want to find out how old rocks are, so we can try to figure out how old different rock formations are that we find. So I've got a nice stratified layer here that you can see in the Grand Canyon, and you can literally follow things back in time as you go deeper. And things that we use for this purpose include uranium-238, which has a half-life of 4.5 billion years. Uranium-238 decays into lead-206. So we know that the stable type of lead is lead-208. So if you have a rock sample which doesn't have lead-208 but does have lead-206, then the sample has lead that came from 238 decay. You can look at potassium-40 going to argon-40. So that's a positron emission and an electron capture. It takes 1.25 billion years for that to happen. So in order to measure this, you actually have to crush the rock and look for the argon in it, because of course argon is a gas, and so you need to release that gas, because that gas otherwise would just float off into the atmosphere and be gone. Okay. What about rubidium-87 and strontium-87? So rubidium decays into strontium. And so if you can find a rock with rubidium in it, you can check the strontium levels and see exactly how long that thing has been out there, because it takes 48.8 billion years for that spontaneous decay to happen. So the oldest rock that we have been able to radioactively date was 4.4 billion years old. That being said, we think the Earth is about 5 billion years old, so it all sort of fits. There is some controversy about the accuracy of this type of radioactive dating, but everybody can kind of agree that yes, the older things are found further down. This makes sense. Hooray! Okay, so let's try to do a calculation involved with the radioactive dating. If we have an igneous rock, which contains 8.27 times 10 to the negative 6 grams of uranium-238 and 1.07 times 10 to the negative 6 grams of lead-206, much, much smaller amounts of lead-208, which indicates that we mostly started with the uranium-238 to make the lead, determine the approximate age of the rock. So let's go back to our nuclear equations. In order to figure out the balance of this stuff, we know that we have to put it in moles, because our nuclear decay equation is a mole-to-mole ratio. So you go ahead and you divide the mass of uranium-238 by 238 grams per mole, and you get 3.47 times 10 to the negative 7 moles of uranium-238. And the current amount of lead-206 is 1.07 times 10 to the negative 6 grams divided by 206 grams per mole. You'll note that we're using the mass of that radioactive particle, not the mass, the average mass of lead or uranium. We want just the particle we're looking at. Okay, so anyway, we get 5.19 times 10 to the negative 8 moles of lead-206. Now, the amount of lead-206 we're going to attribute entirely to the radioactive decay of uranium-238. So in order to find the original amount of U-238, we're going to add the moles of U-238 that you presently have to the moles of 206, lead-206 that you have in the sample. So there you go. And we have 3.99 times 10 to the negative 7th moles of uranium-238. At this point, we can use our fractions. We can use our original amount, N0, 3.99 times 10 to the negative 7th moles of uranium-238, and our amount we have right now, which is 3.47 times 10 to the negative 7th, sorry, in order to figure out how much time it took to get to that point. So we have our lambda equals 0.693 over T1/2, and we get 1.4 or 1.54 times 10 to the negative 10th years for that to take place. Then we go ahead and we plug that into our N ratio thingy. And I've simplified it a bit based on what they have in the book. You can go through the algebra yourself, or you can look in the book and see a similar calculation. Long story short, we get 9.1 times 10 to the 8th years, which is 918 million years, which is a long time. To summarize, radioactive decay has first order kinetics, where T1/2, the half-life, is equal to 0.693 over lambda, which is the period. If you want to calculate how much you have left at any given portion of time, you take a number of stuff for that period of time is equal to what you started with times e to the negative period times time. Half-life is the amount of time it takes for 1/2 of the original material to react or to be gone. Some isotopes are more stable than others and can be used for radioactive dating. Carbon-14 dating is done for living things. For rocks, we might use U-235 ratios versus lead. We might use potassium to argon-40. We might use rubidium to strontium-40, or sorry, 87. But all of these are practical applications of radioactive decay.